Since we are doing paleoclimate, we might as well see if climate change has played a role in our own evolution, right? And related to the beautiful concept of El Nino that we have learned. So here is the reconstruction of vegetation looking at the East African region going from 5 south to about 15 north. And you can see the various names here, the lakes, Tana, Turkana, Baringo, and other places. The time goes back to 15 million years to the present. The main thing I want to emphasize here is that the vegetation types over the East African region has changed over time from open woodlands during the 10 to 15 million years ago. Then it changed to this lush green forest from 10 to 5 million years ago. We won't go into the details other than to say that this is obviously related to orbital forcing, but also to tectonic changes, small tectonic changes, because remember that the Himalayan mountains rose to their level around here, and the monsoon circulation got set up. So East Africa gets 2 rainy seasons now during the so-called intermonsoons of the Indian summer monsoon. So during March, April, and October, November, they call it the short season and the long season, and there are also African words. Nonetheless, it got lush green forests, and then the vegetation changed to dry woodlands, open woodlands, and savannas and grasslands, and so on. Okay, so the changes have to be explained here. Are not completely related to orbital changes. There are multiple theories for it. We will look at one of them, and the argument also is that this change from a green forest which is thicker, lots of food nearby, to this open woodland and grassland which has got less food, and you have to walk further to find food, or you have to run further to get away from predators. In the forest, you can quickly climb a tree or get escape in the thick forest, but on this kind of vegetation, that's much harder. So the idea was that this is what led to bipedalism, because you can run much faster when you're upright on 2 legs. Okay, then there are additional theories that the skull connects differently to the spine when we are standing up, and that allowed the skull to grow larger and the brain to get bigger, assuming we have larger cognitive abilities than our relatives like chimpanzees and other primates. That's your call. So that's just something I want to mention. But getting back to climate, there is evidence from ocean sediment cores in these regions of coastal upwelling, open ocean upwelling, and the east-west sea surface temperatures. Lots of nice papers written by Alexei Fedorov and his colleagues like Peter Dominical from Columbia University, George Philander we mentioned before, arguing that the western equatorial Pacific has remained somewhat same over the last 5 million years, but the temperatures here used to be almost the same as the West Pacific, so the temperature gradient was relatively flat. But since about 2 million years ago, the east has cooled and the coasts have also cooled, including this coast here. So the east-west temperature gradients have gotten stronger in the last couple of million years. And why is that important? Basically because this configuration that we are in now, with a strong east-west sea surface temperature gradient and a shallow thermocline in the east, gives us El Nino that we talked about. Okay, during an El Nino, East Africa gets more rain. Remember the teleconnections of El Nino? Of course, it's also related to what happens in the Indian Ocean. Nonetheless, El Nino induces rainfall anomalies here. So if you had a permanent flat gradient during these times, then presumably East Africa would have been drier. which would explain the drying here. Okay, so growing from green forests to dry lands, woodlands, and grasslands. Why would that happen? Why did this change happen? There are many theories. One of the theories that I'm vaguely involved in argues that the Galapagos, who also move, Galapagos are these volcanic islands that come up in the middle of the plate because the magma bursts through, but the plate is moving, so the magma supply stops and the volcano becomes dead, and then it can collapse. So the islands keep moving. So when the islands intersect the equator, they change the time scale of the El Nino. Presumably they go from every 2 years to every 4 years, or 4 to 7 years. They become less frequent, which would explain the drying here. The other theory is proposed by Mark Kane and Peter Molnar, a very nice paper, that argued that based on the calculation that Australia is moving north at about 3 centimeter per year, if you go back to these times, New Guinea and Australia would have been further south, and this pathway would have been open. That would send the warm waters here and could potentially affect rainfall over East Africa. Okay, so it's not yet confirmed, but the main story is that continental drifts have changed a regime shift in a climate over East Africa, and that could have been critical in the evolution of bipedalism, and hence maybe us from our relatives of the time. Okay, this is the so-called permanent El Nino, where the gradient is much flatter. So today's normal conditions here, with colder temperatures here, strong sea surface temperature gradient. The permanent El Nino of the Pliocene-Pleistocene period 3 to 5 million years ago would have looked like this, with the warm pool extending much further east. The cold temperature here is almost disappearing. Obviously, you would have to have corresponding changes in winds, etc., which obviously will come along if you flattened the sea surface temperature gradient, as we talked in the case of El Nino. Other evidence from the warmer Miocene Pliocene state before, it goes like this. So it's a modulation of the current condition, with more east-west contrast than during the permanent El Nino, but less so than the present. So East Pacific and this sea surface temperature gradient continue to play an important role in climate at various time scales, from El Nino time scale to these permanent El Nino type time scales, and in global warming, as we talked about with respect to global warming pause and the heat uptake in the East Pacific. So for that reason, this climate change is very important, and this is just to remind us that the ITCZ, SPCZ, and the SST distributions of the present day tell us that the mechanism could be what Philander always argues, that heat uptake here and heat loss here may be balanced by moving the thermocline up and down here. So you can change the winds here and move the thermocline and change these heat losses, or you could have glaciation changing these temperature, as we talked about in the last glacial maximum, and that would force the heat uptake here to change for the global balance and move the thermocline, hence change the El Nino character. Okay, so you can see now how all the ocean atmosphere dynamics and the various time scales are coming together to produce climate variability and climate change. Not a very strict definition of climate change, but definitely big changes compared to the present climate that we have. That's the main point about climate change, how things change.